Well, anyway, so I need to check the attendance first. Okay. 20 Raymond Cooley. 20 Raymond Cooley. 20 Raymond Cooley. 15 Aradin Ghana. 15 Aradin Ghana. 15 Aradin Ghana. 17 Noor R. Mohammed Bear Dibikov. 17 Noor R. Mohammed Bear Dibikov. 17 Noor R. Mohammed Bear Dibikov. 34 Mohammed Syed Dama. 34 Mohammed Syed Dama. 34 Mohammed Syed Dama. Okay. 5 Masudu Zaman.
Yes,
5.
Doctor, I'm here.
Okay.
Yes, Doctor, I'm here.
Yes, I hear you. Yeah. 29 Ibrahim Rob Job. 29 Ibrahim Rob Job. 29 Ibrahim Rob Job. 30 Mohammed Therma Kier.
I'm here,
30.
Lashi.
Okay. 5 Mikhail and Safa.
Yes, Lashi, I'm
5.
here.
Okay. 6 Solomon Carleton. 6 Solomon Carleton. 6 Solomon Carleton. 8 Sador Dadajonov. 8 Sador Dadajonov. 8 Sador Dadajonov. 10 Temur Marik Daminov. 10 Temur Marik Daminov. 10 Temur Marik Daminov. 12 Christ David Kirgerov. 12 Christ David Kirgerov. 12 Christ David Kirgerov. 14 Hasp Rahman Noor. 14 Hasp Rahman Noor. 14 Hasib Rahman Noor. 15 Mehrab Hossein.
Yes, Lashi.
Okay.
Laoshi,
Yes. Who are you?
I'm number 12.
Number 12 Christ David Kirgerov.
Yes.
Okay. Okay.
Lashi number 6.
You are Solomon Carleton.
Yeah, number 6.
Okay.
Hello, Lashi. I'm also here. I joined a bit late. Sorry.
So who are
I'm
you?
number Ibrahim, number 29. I
Number
think the second one.
29 Bislam.
No. Ibrahim Roba. F101.
F101. Oh. You are
Yeah.
you are Ibrahim Robert Job, right?
Yes.
Okay.
Exactly.
Oh, Lashi, I'm also here. Number
Who are
22.
you?
Number
22.
22. Ibrahim K. Kumar.
22. 22. 22. Ibrahim. Wait a second. Wait a second. Ibrahim. Yeah. You are F1906 or 01?
I'm F19030122. F19030122.
So you are Ablahim K. Kromas, right?
Yes.
Yeah, okay. Yeah, I haven't come to here yet.
Oh, okay.
Okay. Okay. 21. Gentler feeders. 21. Gentler feeders. 21. Gentler feeders. And then, okay, yeah. Ablasim, you are here. Okay. Then 25. B. Cell feeders G. Russell. 25. B. Cell feeders G. Russell. 25. B. Cell feeders G. Russell. 26. Solomon K. Sawyer. 26. Solomon K. Sawyer. 26. Solomon K. Sawyer. 29. Bethlehem Tirahan Mamo.
Yes, Laoshi, I'm here.
Okay. 30. Next, Laiken Asifa. 30. Next, Laiken Asifa. 30. Next, Laiken Asifa. 31. Valery Butek. 31. Valery Butek. 31. Valery Butek. 22. Oh, sorry. 32. Anna Akulova. 32. Anna Akulova. 32. Anna Akulova. 33. Lavan Takabo.
Yes, Laoshi.
Okay. 34. Benwar Ikram. 34. Benwar Ikram. 34. Benwar Ikram. 36. Azamat Karimlin. 36. Azamat Kariblin. 36. Azamat Kariblin. Okay. Okay, let's move on to today's lesson. Let me share my screen. Okay, can you see the slide?
Yes, Laoshi.
Okay, so let's okay. Okay, so before move on to today's new content, okay, let's firstly have a brief review about our Thursday's lesson. Okay. So in Thursday, okay, we have our first lesson of this course. So we introduced what is the embedded system. Okay, so we have discussed that. Okay, there are a lot of embedded products all around our daily life. Okay. So they can be categorized mainly into 6 categories, including the consumer electronicals, medical electronicals, military and aerospace electronicals, industrial control electronicals, vehicle electronicals, and network communication electronicals. Okay. So remember one thing, okay? Embedded products is also you can imagine that it is considered as a tiny, maybe sometimes maybe not that small. Okay, these are also a computer. Okay, but just a specialized designed computer. So the purely mechanical things, mechanical device, not belongs to embedded systems. Okay. It must be controlled by some computer system. So it could be an embedded device. Also, okay, then we give the definition of the embedded system. Okay. So here we mention that the embedded system is a specialized computer system. So which means that anyway, it's still a computer system, but it has its own specialized features. Okay. So firstly, okay, it is application centered. So which means that okay, our embedded system must combined with a certain application. So which means that our embedded device okay, is really designed for a certain application. Okay? For instance, maybe it is used to control a machine in a factory, or it is used as a camera, okay? Or okay, it is as a system for your cell phone. But anyway, okay, it is application centered. So for such embedded devices, okay, it needs a corresponding embedded system. Okay? So because of the embedded device is application centered, so the system, okay, operating system to manage it is also application centered. Then it is computer technology based, but with reducible software and hardware. Okay. Because that still, okay, it is kind of computer system. Also, okay, the technology for the embedded hardware, okay, is also based on the computer technology. But in general speaking, okay, we know that the first computer, the first electronic computer, okay, came out at 1945, right? By US, okay. So after that, okay, the embedded system and the embedded device comes out. Okay, so it is still based on the conventional computer technology, but with reducible software and hardware. Okay, why we say so? Okay. So firstly, it has software and hardware, okay, like a normal computer. Okay, we know that a computer system has hardware and software. Okay. But okay, because of the design goal of an embedded system, okay, it usually just need to facilitate one single function, so that it does not need so many software and hardware. Okay. And usually, okay, as the third feature says, okay, it has, because of that, it has strict requirement on the function, reliability, cost, volume, and power consumption. Okay, because of these strict requirements, we have to reduce the needed software and hardware. Okay, in general speaking, the software and the hardware in an embedded system should be as less as possible. Okay, so we should just have the minimum software and hardware to run, so that we can reduce the cost. Okay, we can reduce the volume of the device. We can reduce the power consumption. Okay, and usually, okay, with less components in a system, so we know that sometimes, okay, we can say that the robust, okay, or the reliability of the system will be increased. Okay. Generally speaking, when comparing with a conventional computer system, okay, the big architecture is similar. Okay, they both have software and hardware, but when come to the details, okay, an embedded system, okay, either on the software side or on the hardware side, okay, it has much less software and much less hardware. Okay. Then we also summarized the 5 characteristics of the embedded system. Okay. So firstly, microkernel. Okay. So why an embedded system should have a microkernel? Okay, because that usually the embedded system have very limited resources. Okay, limited ROM to store the code, limited RAM to load the code into the memory. Also, usually have very limited power resource. For instance, okay, an embedded version of a Linux system can have only about 200 kilobytes its size. Embedded version of Linux kernel, okay, its size is about 200 kilobytes. But okay, you can check the Linux kernel, for the PC, okay. Because Linux is open source, right? Okay, you can check them. Yeah, nowadays the Linux kernel, at least it's about roughly 100 megabyte. Okay, and you can see that the size of them has much different. Okay. Then the specialty. Okay. As I just mentioned that, okay, the embedded system, okay, is application centered, okay, so that, okay, each embedded device is designed for achieve a certain goal, okay. In other words, one embedded device, okay, achieve this goal, so that this system is also specially designed. And it cannot be usually, okay, in most of cases, one type of embedded system cannot be run on other type of embedded devices. For instance, okay, your cell phone, right? If your cell phone is an Android phone, okay, it must have an Android-based OS, right? Okay, of course, this Android OS cannot run on the iPhone, right? But not only that, such Android-based OS can even not run on another and maybe it cannot run on another Android phone. Okay. Then the reducible, okay, we just discussed, right? Because of the strict requirements of the volume, power consumption, and other resource problem, okay? So that the embedded system has reducible software and hardware. Okay, it is a specialized operating system, okay? So that, okay, it is firstly, it means it is an operating system. But secondly, it is specialized. It's because that it is designed for certain functionality. Secondly, it is designed for certain devices. And also, okay, because of this reason, the embedded system has much difference than the conventional computer system. Finally, because of the above characteristics, okay, so the development of the embedded system, okay, is much different, okay. Since that an embedded device, okay, usually have very limited resources, so itself usually does not have the ability to develop and encode, okay. So, for instance, some embedded devices even do not have any human input device, okay, because that lot of embedded device, for example, okay, the camera, it read data, use its own, for example, the sensors and other things, okay. So you do not have any human input interface. So that actually, as we mentioned in the last lesson, that we actually develop the embedded application and the OS on a computer, okay. And then after the compilation, okay, then we can migrate this code, this compiled code to the embedded device. But because such development mode is somehow much different than the conventional development. So because that in our PC, okay, if we want to develop a PC application, right, okay, we can simply coding on the PC and compile on it and then run on it. So the debugging, testing are very convenient. However, in the case of embedded development, okay, some IDE provide some simulator for debugging and testing, okay, but still, okay, it may not can reflect the real details of the hardware. So it means that even your code can pass the simulators debugging and testing, okay, it might cannot work well on the real embedded hardware. Okay, so it is different. Okay, let's move on to today's new content. So today we will discuss the second section in this chapter, okay. The architecture, embedded architecture. So what is the architecture of a computer system? We should have at least hardware, right? Okay. Then please try to and please answer me this question. Okay. When you learn the operating system course, okay, the teacher should have told you about what is the architecture of a computer system, right? So the bottom is hardware. Then what is running on the hardware? Anybody
Kernel
can?
software or embedded software like assembly software.
Yeah. So
Then,
what kind of So what kind of software will run on top of the hardware?
maybe
Yeah, you are right. So of course, you are right. Firstly, it is the software that is running on top of the hardware. Yeah, but which kind of software run on top of it?
assembly language.
Assembly link? No, not assembly link.
Operating system.
Yeah, right. Operating system, right. Okay. Yeah, it is the operating system run on top of the hardware, right? Then what kind of software then running on the operating system?
Application software, presentation software,
Yes, right.
package software, etc.
Right. Yeah, generally speaking, the architecture of a computer system, right, have 3 levels. Okay, the bottom level, okay, is hardware. Then the second level is the operating system. Then the top level, okay, is the application. Okay. So okay, but generally speaking, okay, the OS, okay, the operating system and the application. So we call it the software. And we know that without the software, so that actually the hardware cannot be used, right? So that only with the software, okay, we can actually use the hardware. And the similar case apply here, right? So also this architecture, okay, works for the embedded system, especially in this case, in the case of embedded system, okay, usually we do not actually have the application level software. Lot of small embedded device actually in the software part, okay, it just have a operating system, okay, to operate the hardware. So here, okay, let me see the architecture of the embedded system. Okay. So okay, at the hardware, is that okay? Here is one thing called the embedded MPU. Okay. Okay. So remember? So no, not remember. Sorry. So just one question. So what is the core component of a computer's hardware? What is the most important hardware among a computer?
Transistor.
Pardon? Sorry?
Transistor.
No, not transistor.
Transistor.
Not the transistor.
CPU?
Transistor is just a part of another, just a part of another hardware.
CPU.
I think the
component.
motherboard.
No, not the
No,
module.
CPU.
Yeah, CPU, right? Yeah,
Processor.
right. Yeah, so CPU, yeah, the
CPU.
central, yeah, the central process unit, right? It is the most important things. Okay, not most important component among a computer's hardware. Okay, because that the CPU, right? It is the CPU that can process the instructions, right? In other words, okay, it is the CPU that can really run the software. Of course, it can run the software not because that not only a CPU can run a software, right? It also needs other hardware, yeah, other peripherals. Okay. So here, the MPU, okay, MPU is short for microprocessor unit. Okay, so by it means, right, you can guess what is that, right? It is the processor for embedded device. Actually, it is involved from the computer's CPU, okay, but it works in the embedded device. Also, despite of the core component, the MPU, okay, an embedded system hardware also need the peripherals. But here, the peripheral device, okay, in an embedded system, okay, is usually much less than a conventional PC. Okay. So here it usually refers to something like a bus, I/O, a ROM, a RAM. Okay, not something like but for the screen, keyboard, mouse, graphic card, sound card, these things are usually not. Oh, let me see, NUR. Let me see. Okay, I say okay. NUR 14. Okay, I got it. Okay. Anyway, sorry. So anyway, okay. The embedded system also has its processor and peripheral devices. Okay, this is the hardware side. Okay. Then on the software side, okay, it also has an embedded operating system, and for some powerful embedded system, like your cell phone, okay, it can have applications. Okay, but here, not every embedded system have application level software. Okay, please remember that. So in general speaking, you can still consider that the conventional computer system architecture still works for embedded system, but for the details, it has they have different they have some difference. Okay, so here we know that the CPU, okay, is the core hardware component for a computer. Okay, then also, okay, here we need to know that the processor or embedded processor is also the core component of the hardware. Okay, then what is the difference, okay, between an embedded processor and a computer processor? Okay, remember that. Okay, we just have a course review there about our last lesson and mentioned that for embedded system, okay, it has strict requirements for the function, reliability, cost, volume, and the power assumption. Okay, so because of this reason, so the embedded processor has much difference from the computer processor. Okay, so and let's discuss the embedded processor. Generally speaking, till now, there are 5 typical architectures of embedded processor. Okay, so when we say till now, okay, it is because that okay, not at the very beginning, okay, they are just MCU and MPU, okay, of for the embedded processor, while the DSP, okay, SoC and SoPC, these architectures appeared with the development of the semiconductor technology. Okay. You know that you know the Moore's law, right? Anybody can answer me what is Moore's law?
I know, but now I forget. I can't remember right now.
Anyway, I don't let you to. Okay. Anyway, so just a question. Okay. So you know that in general speaking, Moore's law refers to that. Okay, with the development of the semiconductor technology. Okay, so the speed of a processor, okay, will increase exponentially. Okay. So that's why the processor speed can become quicker and quicker. Okay, it's because that given the same size of a chip, okay, nowadays the people can integrate more cores and more devices on a single chip. Okay, so that's why the processors running speed can become so fast today. Okay. But it seems that in recent years, okay, because some physical limitation, okay, so the Moore's law also reaches some limitation, okay, because at it seems that the chips, okay, if you want to make some very tiny device on it, okay, maybe some nano things on it, it is very hard. So that nowadays, okay, the processor speed cannot follow with Moore's law, okay. But maybe with some development of physical science, okay, we can still see more powerful processor in future. Nowadays, our process speeds are usually increased by integrating more processor cores on it. Okay, you know that nowadays, okay, your computer, your cell phone, okay, one processor usually contains 2 cores, 4 cores, 8 cores, or even more cores, right? Anyway, okay, so let's see these architectures of embedded process. Okay, let's start from the MCU. Okay, MCU. Okay, it is short for the term micro control unit. The microcontrol unit has another name. Okay, single chip computer. Why we say the single chip computer? Okay, so it means that okay, it integrates an entire computer system, okay, on one chip. Just speaking, okay, a single chip computer, okay, will integrate ROM, RAM, bus, timer, watchdog, I/O, port, EPROM, and flash together. Okay. So here, okay, we said the ROM and the RAM, right? Okay, you know what the functionality of them, right? The ROM need to store the code, okay? Store at least it will store the code of the embedded OS. The RAM, it will be used to run the program. Then the bus, okay, the bus its usage is to transfer data, okay, so that with bus, okay, the devices, these components can be connected together. While timer and watchdog, okay, so a lot of embedded device, okay, or embedded system, okay, it is actually time driven. You know, time driven, right? It means that it may run something at a given time interval or at a certain time. Okay, so the timer and the watchdog are used for it. Then the I/O port, okay, and this one is for the input and output. Okay, then the EPROM and the flash are used to contain more applications. Okay. So so why we say this is a microcontrol unit? Okay, remember what is the full name of the CPU? Okay, CPU is a central processor unit. Okay, but here it is a microcontrol unit. So firstly, micro. Okay, micro we can easily understand. Okay, because that these things are integrated on a single chip. A chip is very small. Okay, we can say it's micro. Okay, but when we say control, okay, it is because that the MCU, okay, are usually used in industry area. Okay, especially in the factories. Okay, MCU are usually used to control the automation machines. Okay, so with the integration, okay, so the cost, reliability, power, and other things are limited. Okay, so that it can be used directly on a factory machine. Okay, then the MCU, okay, combined together, okay, it will form an industry control system. Okay, But here, if you notice that, okay, MCU, it can control the factory machine, okay, but the industrial control system, yeah, MCU is part of it, but still, the industrial control system are usually not only consist of the MCUs, but also may include a server. Okay, the here a server is not an embedded system; it's usually a computer system. Please remember that. Okay. So the typical model of MCU, okay, is including the type 8051, okay, then 8096, and the C8051F. Okay. This is some classical model of the MCU. Then the DSP. DSP, okay, refers to digital signal processor. So by the name, okay, we can know that it is not designed for control. Okay, it is designed for some special purpose. So digital signal processing. So especially it usually used for real-time signal processing. So to do so, okay, the DSP, okay, has some special instruction structure and algorithm, okay, that are designed particularly for this process. So why are the DSP, okay, this process used? Okay, they are used in the digital filtering, FFT, and spectrum analysis. Okay. Okay, so till now, okay, you may still wondering, okay, what exactly where we will use the DSP, okay? Okay, let me show an example. For instance, okay, you use a cell phone, okay? Sometimes, okay, some apps on your cell phone may ask you to show your face, okay, and to recognize whether the user is you, right? Okay, it needs to recognize your face. Okay, so you know that to recognize your face, we need use the image recognition technology. Then how to do that? Okay, in the image recognition, okay, the FFT process, okay, is actually is one of the necessary steps of the image recognition. Okay. So for embedded device, okay, that have the functionality to recognize the image, okay, or to process the images, then the DSP is very needed. Also, okay, if the embedded device need to recognize some other biometry information, okay, for instance, your fingerprint, okay, I think some of your cell phone, right, can have the functionality to recognize your fingerprint, right? So to recognize the fingerprint, okay, it's usually use the DSP. Okay. So actually, you see that, okay, because actually originally the digital filtering, okay, FFT and the spectrum analysis, okay, these functions, okay, are specially developed with than conventional MPU, okay, we will discuss it later, okay. But you know that to do these things, okay, using a conventional processor, okay, the efficiency is not good. So that's why, okay, because that for this purpose, like digital filter, digital signal processing, okay, we have to use the very specialized algorithm. So that the instruction structure and algorithm and code should be specially designed. So that's why we have to develop separate DSP. Okay. Okay, so let's have a 5 minutes rest. Okay. Let's come back. So here, we are discussing the DSP. Okay. So why why we have to use a separate DSP, okay? Because that, okay, for these things, okay, digital signal processing, okay, in our computer, right? We do not use a special computer to do these things, right? Okay. But it is because that our computer, okay, usually have much powerful processor and enough hardware resource to handle, for example, the image processing, the signal processing, and so on. But in the case of the embedded system, okay, it has limited resources, so that everything run on it must have the optimization. Okay, so in this case, okay, the digital signal processing algorithm, okay, and the related instruction set, okay. Once it is optimized, okay, it is hard to run on a conventional embedded processor. Okay, so we have to use a separate DSP. Okay. Also, because of the development of the semiconductor technology, so that DSP, okay, can be used as a core of an embedded processor. Okay, so conventional MCU or MPU, okay, can be integrated with one DSP or DSPs, okay, on a single chip. So anyway, it's still because of the development of the semiconductor technology, so that we can have much more powerful embedded hardware. So the typical model of DSP, okay, is TMS 320C 2000 or C5000. Okay, then come to the MPU, okay. The MPU, okay, as I mentioned, okay, it is involved from the CPU, okay. Microprocessor unit, okay, is involved from the central process unit. Okay. So in general speaking, okay, it is a conventional embedded processor, okay, with high performance. So, but when comparing with, of course, when comparing with the computer's processor, okay, it usually have less volume, okay, less weight, okay, and less cost. The word length, okay, you know the word length for a processor. Do you know what is the meaning of the word length in a processor? When you learn the operating system course, okay, I'm not sure, okay, whether the teacher told you about something about the processor and the word length. Do you know what is the meaning of the word length in a processor? Anybody can answer this question? Okay, so what is the word length in a processor? Okay, so we know that a processor, okay, either in a computer or in an embedded device, okay, it needs to execute the instruction, right? You need to execute the instructions. So, but we know that the instruction, okay, is actually the 1010, okay. This actually is the bit stream, right? But one program, okay, after its compilation, okay, it becomes the bit stream. Usually, a program have a lot of instructions to be run, right? Okay. So here, the word length means that, okay, the length of instructions can be fit into a processor at one time. Okay, that means that, for example, if the word length of processor, okay, is 32 bits, okay, then it can just run this length of instructions at one time. Okay, of course, if it's a 64 bits processor, okay, then it's at one time it can handle more instructions or longer instructions, right? So of course, okay, for the different okay, yeah, it's a word length, right? I think that the operating system course you may already learn it, right? Okay. So it's because that with the development of the technology, okay, usually the word length of a processor, okay, is become longer and longer, so that the efficiency of a processor, okay, is better and better. Also, okay, an MPU, okay, usually have very rich peripheral interfaces, okay. Generally speaking, okay, you can consider that the MPU, okay, as a conventional processor in the embedded system, okay. It is not designed for some special purpose, okay. Like the DSP, okay, DSP is specially designed or optimized for the digital signal processing, while the MCU, okay, is mainly designed for industrial control and other control purpose. Okay, but here the MPU, okay, yeah, you can think that it is a conventional process, conventional embedded process. Okay, so that it needs to need to be have the facility to support the other peripherals, okay, so that it can accept more I/O device, okay, it can accept more ROM, RAM, and other things, okay. So actually, the processors, okay, which are used in cell phones all belongs to the MPU, okay. Yeah, if, for instance, if you have a 32 bits processor, okay, its bus should be able to transfer 32 bits data at one time. Okay, so you know that the actually the processor in your cell phones are MPU. Okay, actually nowadays, okay, MPU, okay, is the most widely used embedded processor, okay, among all the embedded products, okay, because of the widely used of the cell phone, okay. And also the competition, okay, of the cell phone processor is very harsh, right? Okay. Of course, okay. For instance, okay, the yeah, when you know that the Huawei, okay, the Huawei company, okay, has been sanctioned by the U.S. government, so that before, okay, the Huawei cell phone, okay, are using the processors, okay, produced in US, okay. But nowadays, it have to change the source of the processor, okay. It have to use some processor produced in China, okay. Anyway, that this is some problem, okay. But actually, we have to say that nowadays, okay, the dominant architecture of MPU, okay, is ARM MPU. ARM, ARM, okay. Here, the last one, okay. ARM, okay. ARM is is an England company. Okay, so that the ARM CPU takes about 75% of the global share. Okay, while the MIPS okay also takes certain. I'm not exactly remember what it is. I think it's more than 10%. Okay, with taken by the MIPS. Okay. Then the rest architectures of the MPU okay takes not that much. Okay. In general speaking, the ARM okay ARM architecture okay are very so widely used okay because it has its own advantages. Okay, we will discuss that later. Then the SoC system on chip. Okay, this is a kind of the embedded processor comes out later in the later days. Okay, because of that at the very beginning, okay, the semiconductor technology cannot support such such a processor. So why we call it a system on chip? Okay. So that it means that okay, we can integrate almost everything okay, in a single chip, especially you ask ARM processors. Generally speaking, okay, actually we will try later. Okay, I'll explain it a little bit about ARM processor. Okay, ARM company actually is not itself. We do not produce any processor by itself. It's just produce the design of the processor. In other words, okay, it sells the design of the processor and the real production of this ARM processor are other companies. Okay, so that in general speaking, so far, yeah, we can see that the ARM's processor okay is most advanced. Yeah, we can say that. Okay, come back to SoC. Okay, SoC, okay, it can, despite of the processor, okay, it can include other devices. For example, the DSP cores and the peripheral devices. Okay, here the LSI, okay, refers to the large-scale integration. Okay, remember, okay, what is the let me say the third generation, okay, of the computer. Okay. It is the third generation of computer is a large scale integration okay, computers. Okay. It is because of the development of the semiconductor technology. Okay. So it also works for the embedded system. So the SoC, okay, you can say that is somehow a high-end product. Okay. So SoC, okay. When we designed, we can use some special design software like the EAD and so on. Okay, so the user okay can design out the entire embedded system okay with SoC because the SoC can be considered as a single component when designing an embedded system. Okay. So after the user have designed the entire embedded system, okay, and then use some simulator to check whether the system can really works. LIS means that the large scale integration is a technology. DSP is a processor. Is different. LIS chip means that it can integrate a lot of things, okay, in a single chip. Okay, you can check it. You can check the development of the semiconductor technology, or you can check the development of the computers. See the third or fourth generation of computers. Okay, it is LSI. Okay. Okay, then. So why the SOC is important? Okay, because that with LOC, okay, we can just use a single SOC as a as a single function component. The user don't have all the designer of the embedded system don't have to take in the details of the details on a chip into consideration. These things are already be solved by the chip producer. Okay, they just use an SOC. Okay, for instance, here this piece of SOC, okay, are used for the image recognition. Then another SOC, okay, are used for human interface. Okay, then this SOC, okay, are used for computation. So we can design these things like that. Okay, so somehow, okay, like when you do the programming, okay, you export some external library, right? Okay, so it's like that. Okay, you simply use some API, okay, to call the functions in these libraries. You don't care about the detailed implementation of these APIs, okay, of not API, not the functions behind the APIs, right? You just use them, and you know the function of this, you know the functionality of these APIs, and that's okay. Okay. So here, okay, the designer of the embedded system don't care about the details, about the SOC chip. They just care about the functionality of SOC. Okay. So after the implementation of the SOC, okay, the design of the embedded system become much easier than before. Okay, because before the designer must consider the design on a chip. So you know that for a chip, there exists a processor, bus, the I/O device, and other peripherals. Okay, so you also need to think that all these things can work together. Okay, this is also very time-consuming and error-prone work. Okay. Then the SOPC is a much more powerful chip than SOC. So here, SOPC refers to the term system on a program chip. Okay, so the additional functionality, okay, is programmable. Firstly, it has all the advantages of SOC. But now we can directly programming the chip. Okay. In general speaking, we use FPGA for the implementation. Here FPGA means the field program gate array. So means that nowadays, okay, the SOC, okay, we can even do some programming to implement the needed function by ourselves. Okay, so before the SOC just provide, okay, as a certain function. Okay, but now, okay, if we think that okay, this function are not enough, okay, so we can use our own code, okay, to and with this chip, okay, to achieve more functions. Okay. So here the field program gateway, okay. You know the gate. What is the gate? Do you know that? Yeah, okay. Actually, this one refers to okay. Generally speaking, you can think that the gate is somehow like with electricity. Okay, then it means one. Without then it means zero. Okay, this is the basic gate. Then some complex gate can have more logical calculation, okay, like and, or, okay, and inclusive or, and so on, okay. So with this basic gates, okay, we can do the programming, okay. But of course, this is the basic hardware unit for the FPGA. Okay. But for the coding, okay, we have the software for development. We don't have to write. We don't have to design design with the gate. Okay, that is so harsh. Okay, actually we have the FPGA has its own programming language. Okay. Okay, so let's see the history, brief history of the embedded processor. Okay, so at the very beginning, okay, at the 1970s, okay. Yeah, you are right. Arduino is based on SOPC architecture. You are right. So you have some experience using Arduino? Yeah, Arduino. Yeah, Arduino is Arduino actually is a software that can operate these chips. Okay, or actually not only a chip, actually it operates on the board. Okay. So the Arduino's coding is on the computer. Okay, the computer can connect to some embedded boards, okay, and we can program and for our with our own purpose. Okay. Okay, so at 1970s, okay, firstly the MPU comes out. Okay, yeah, it's still proposed by the Intel. So Intel not only produce the conventional computer processor, it also produces the embedded processor. Okay, so when you see some x86 processor, okay, it might be an embedded processor, okay, not a computer processor. Then the MCS at 1980s, okay, then at 1990s, the ARM processor comes out. Okay. When at 1998, okay, the first DSP are invented by the TI company. Okay. After then, okay, the SoC and SoPC comes out. So here in this class, okay, where we are mainly focused on the MPU, okay, because that the MPU is the most used embedded processor in embedded system. So, okay, like the CPU, okay, we know that the CPU, okay, has two architectures, right? One is the CISC, another is the RISC, okay. CISC, okay, refers to the complex instruction set computer, while the RISC refers to the reduced, okay, instruction set computer. No. So because the MPU is involved from a CPU, okay. So here we also have the two different architectures, okay, CISC and RISC. So what is the advantage of the CISC? Okay, so the CISC its instruction set contains many powerful instructions and have different kinds of addressing. Okay, So in general speaking, okay, the CISC processor, okay, can directly achieve more functionalities, okay. But of course, it has its own disadvantages. So we say that, okay, its instruction set in CISC, okay, it has many powerful instructions. But for these powerful instructions, okay, they usually have different lengths. Okay, we know that, okay, a processor has a certain, okay, word length, okay, and we know that all the modern processor, okay, either in computer or in embedded system, okay, they use the pipeline execution, okay. So with the different lengths, okay, these instructions are inconvenient to be run as the pipeline. So that its running efficiency, okay, are not that good. So a typical, okay, a typical CISC, okay, MPU is the Intel x86 series. Then another architecture, okay, is the IISc, okay. So when comparing with the CISC, okay, IISc has limited simple instruction set, okay. So in this instruction set, okay, it contains only the most frequently used instructions. So the powerful but complex instructions in the CISC set, okay, are not included here. So the IISc, okay, it has a fixed instruction set and format, and also has lesser addressing models. So, okay, with a fixed instruction length and format, it is very convenient, okay, for the instruction to be executed in pipeline, okay. So it can have the pipeline optimization and with short execution time. This is the advantage of the IISc. Of course, okay, the IISc also has its own disadvantages, okay. In general speaking, okay, this instruction comparatively have less functionalities than the instructions of the CISC. So to mitigate this problem, IISc MPU, okay, is usually equipped with a large number of general registers. So typical MPU with IISc, okay, are the MIPS MPUs and ARM MPUs. So as we just mentioned, okay, both IISc and CISC have their own advantages and disadvantages. Okay. So now some processor producers try to combine them together, okay. So that some hybrid architecture that integrates the advantages of IISc and CISC architectures together, okay, are implemented. Okay. So for some type of the Intel processor, okay, they actually use such hybrid architecture. Okay, so the MPU, okay, is a processor, okay. So not at the very beginning there, of course, one processor, just one processor core. Okay. nowadays, okay, one processor may have multiple cores. Okay? So the chip manufacturer, okay, actually produce chips based on the processor cores. So the processor cores, okay, including the ARM cores, XL cores, OMP, okay, x86, MIPS, PowerPC, okay. PowerPC usually refers to the IBM and Motorola. Okay. Okay, so here let me introduce the ARM chips. Here are the ARM chips. So this ARM architecture, okay, as I just mentioned, okay, it takes more than 60% of the global share of the MPU. Okay, so it is the most widely used MPU. So the ARM company, okay, just design the ARM chips. Okay, so it is an IP supply. So here IP refers to the intelligence property. Okay, not the IP address. Okay, so the ARM company itself does not engage in chip production, while it just supply the chip manufacturer with its own design license. Okay, so it licensing some manufacturer. Okay, so you can produce the certain type of ARM chips. Okay. Okay, so the major the major semiconductor manufacturers all over the world, okay, are buying the design of the ARM MPU, okay, and also, okay, they will after the purchase of the design, okay, they will add their own peripheral devices, okay. So that because that the ARM, okay, the ARM MPU, okay, is just a processor, okay, it also needs some other peripherals, okay, to achieve the certain goals of the manufacturer. So the main characteristics of the ARM MPU is that the low power consumption, low cost, but with high performance. And because of this good characteristics, that the main semiconductor manufacturers all over the world actually are they are cooperates with ARM company. Okay. Okay. So exactly, okay, what are the ARM? What is the ARM design? Okay, design. So they design the IP core on a chip. Okay, so the IP here is the intelligence property. Okay, not the IP address again. Okay. So here, what is the IP core? Okay. So IP core, okay, usually consists of the transistors, management unit, okay, the exception management system, cache, okay. So actually, the IP core, okay, is the most IP core is not a processor, okay, okay. It is the core of a processor. So in general speaking, okay, the instruction execution, okay, will be executed by the IP core. Okay. Also the decode, instruction fetching, execution, all these steps are achieved, okay, in the IP core. So here, this part, IP core are designed by ARM. While the semiconductor manufacturers, okay, they need to, because they want to use the IP core, okay, they can design their own interface module. Okay. So the interface module, okay, just provide the interface for the IP core to the peripheral devices. Okay. So the IP core designed by ARM, the interface module are designed by the manufacturer itself. Then combined together, okay, this chip. So the ARM, so you see that the ARM company just design part of the chip, not design the entire chip. Okay? They just design the IP core. But the IP core are really the most important part for a chip. It can either the instructions fetching, instruction decoding, and execution, okay, are all done within the core. Then the x86 architecture, okay. So here, when we're talking about the x86 architecture, okay, so of course, we will first think about the Intel, right? But actually, the ARM and the Cyrix are also produce the x86 architecture processor. Okay. So the first processor, okay, is produced by Intel. Okay, we know that is 16. Okay, so sorry. So what's your question? Yeah, right. 886. Sorry, what's the question? You just hands up. So what's your question? You can just so anyway, so you know that yeah, this is the first CPU all over the world. Okay, but you should know that this is a CPU and not the AMPU. Okay, other than in the following days, okay, the AMD and the Cyrix also can produce the CPU using the x86 architecture. Okay. Here, once the embedded system comes out, okay, the Intel, AMD, and the Cyrix also produce the x86 MPUs. In general speaking, okay, those the Intel, okay, AMD, and the Cyrix, they are all manufacturers. They are different than the ARM company. Okay? ARM is a designer, but the Intel, AMD, and the Cyrix, okay, they are both designer and manufacturer. Oh, okay, I know. Yeah, I will take your attendance. Yeah, sorry. But you know you are coming late. Okay. So generally speaking, the x86 MPU, okay, has a good price performance ratio. Secondly, it has very good software compatibility. It because that right nowadays the most of the software can actually use the x86 instruction, okay? So that we also have the software resources, and also there are a lot of development tools. Okay. Then MIPS architecture. Okay. So the full name of the MIPS, okay, is what? Is a micro processor, okay, without interlocked paired stage. So you know, okay, the interlock, right? Interlock, okay. When you study the operating system course, that you should remember that something with the interlock, right? Okay. So in the Intel, okay, in the Intel CPU or in the Intel processor, okay, this interlocking problem are solved on the hardware, but here the interlocking problem are needed to be solved by software. This is different. So, but without the interlock, so interlock means that, okay, for instance, if an instruction A, okay, namely, okay, instruction A use a variable, let's say named counter, okay, the instruction B also use this variable counter, okay. You know that because of the pipeline execution, okay, the execution sequence of the of these two instructions may not depends on it depends, okay. So with when different instructions actually from the different processor, okay, using the same sharing variable, we will facing the interlocking problem, okay. So after the shared variable, okay, may have some problem. Now, deadlock means that because of some wrong programming or some wrong scheduling, okay, yeah, some resource or some variables can never be can never be visited. Interlocking means that here with interlock, okay, we can use this shared resource in a correct way. Okay. So, but here the for the instruction level interlocking, okay, the Intel CPU processor, okay, manipulates it using hardware, while the MIPS, yeah, here you need to manipulate with the software. But okay, the MIPS, okay, similar to the ARM, okay, it also just sells the IP cores, okay, so it's also a designer, not the manufacturer. So in China, okay, so we have the Langsheng processors, okay. So the Langsheng series it actually has a MIPS architecture. Also, okay, maybe some of you have PS, right? Okay. Actually, the processors, okay, the Sony processors in PS also belongs to the MIPS architecture. IP means the intelligence property. Okay. While the power PC, okay, power PC, okay, is a kind of IC, okay, architecture processor. It usually have good scalability, convenience, and flexibility. The most important characteristic of the Power PC is that it's openness. Okay? So it defines an instruction set and allows anyone to design and manufacture processors compatible with the Power PC. So its openness is very good. Also, okay, the related source code of software can be used for free. So currently, the PowerPC are mainly used in the network and the multimedia area. There are also some other architectures of the embedded processors. Okay. You can check it. Okay. Today we end up here. But okay. Time is up. Okay. We stop here today. Bye-bye.
No, sure.
Bye.